and welcome to another video. Today we are going to talk about Minecraft and Wolfenstein. And I had a video that I talked about this already, where we went through how to take a map, take from the image, take some image data, and then create a map inside of Minecraft so we could play Wolfenstein in Minecraft. And in that video I was talking about that there were some Carmacized things in this map format. So John Carmack had did his own compression algorithm and so on. I thought it was really fun to look into that more. And if you didn't think that I would do another video where I actually did that, well, then you're probably new here. Welcome to the channel. I hope that you will stay. So let's look into this. Let's switch over to my screen here. So first off, we have Minecraft, and we have the world below me here, because I spawn above the actual world, but I will be put into the actual map when we load it. And I have taken the map data, parsed it, and then created the different maps. So I can actually load any map. And the reason they compress it is because they wanted to store it on one disk. And we are talking about the old save symbol, the floppy disk. So it's a map data that were like 400 kilobytes in size, and they needed to get it down to 150 kilobytes. So it's a pretty good compression algorithm. So if we look into my Java code here, so this is what I've been playing around with. We have two files. We have one file with the map header data. This tells us pretty much where to find the different maps in the other file. So it's just a bunch of headers and a bunch of pointers into the map data. And it points to different planes and the size of the planes. So we will fetch plane 1 and plane 2. Plane 1 is pretty much the floors and the walls. So that's a very simple part of the map. And then you have plane 2, which is all the objects, the enemies, where you spawn, and so on. So that's the different things. What we need to do with this data, we need to fetch it from the map data. So figure out what part of the map data is the actual data. We will fetch the bytes that is there. So we will go from a particular pointer in the map data to a particular size. Then we will un-Carmacize these map data, and then we do an RLEW, which is another unpacking method. And the RLEW is something that they come up to by their own, and then Carmacized is a little bit taking inspiration from Sieve, but we will look in those later, and then we will send that map to actual Minecraft. We will sleep a second, and then we will fetch the objects and send those into Minecraft as well. The reason I sleep a second is just so I know that all the walls and everything is loaded before I send in objects like enemies, so they don't fall through the floor. So that is pretty much the high level what we need to do. So let's look at each of these parts. We will fetch some data here, some map data. And what we need to do is read the bytes in little endian order. So it's pretty much backwards. It helps with the compression a little bit, so that's the way they are doing it. And everything that you read is in words. So they are not reading bytes, because they needed more than 256 objects, so they needed to do it in words. So they have 65,536 different options. And then we will check the header, and they could have a different header. They have all chosen to use ABCD, and that is one of the keys for the encryption. That is what we will look for in order to figure out what we need to do. So we check that that header hasn't changed here. So this should be true. And then we will fetch the map data in a little bit in the end as well. So the first we need to do is get this offset here and check that that is not 0. So because then we will go to, we will just go out. So we go to this and we'll look at the first map data here. And then we will fetch a particular position of the map offset. So we will jump to that particular offset of the map data. So the first part here is we have this header that we talked about. So that's 2 bytes. And then we have the map. And what we are looking for is ints as an offset. So that's why we are doing ×4. So if we are looking for a map 0 for instance, 0 times 4, then we will take the first int at position 2. If we have map 1, then we will look at position 6 and so on. So we will get the map offset, we will jump to that map offset, then the first 3 ints are the planes offset, and they have 3 planes. The third is not used in this particular option here. And then we have 3 plane length, and those are in word, so characters. And then we will have width and height, which we are not using. Those are probably 64 in each case. That is just the width and height of the actual map. Then we'll take a buffer here of 16 bytes and fetch those, and that is the name of the map. So we can print out the name of the map that we are loading. And then we will, in the case of plane 1, fetch the plane buffer, create one of the plane length, go to the map position in the plane offset in the BB map, and then get all those bytes and then return that. So that's pretty much it. We fetch some map data. And next we will decompress them with Carmac. So if we jump into that function, and here the thought behind Carmac is pretty much that you have a bunch of data like this, and then at some point you have a character, and then you have a length and a number, and then it will look back that many characters in the sequence and then take that many numbers and put in front here. So it's a way of looking at the output buffer that we've already written and see if we can find a couple of words that we want to copy into the sequence next. So it's a way of compressing things by using what is already written. So we will fetch the map data here. So this is the buffer in little endian that we have. See, we will take the first word here and just check the size. So the size of this uncompressed data, and we'll put that into create a buffer of that size so we can actually write it. Then we will get the length of all the bytes. So all the bytes sent in, we have that length. And we will jump over the first length here. So we'll start at position 2. So we will jump over the uncompressed size. And then we will go through the full length of this compressed data. And we will do 2 operations here. We have 2 if statements. The first if statement checks if the second byte, not the first byte, the second byte in the sequence is A7. If the second byte is A7 and we have a length that is longer than 2, so we have more than 2 bytes left, then we will take the current byte, and that is to count how many words we want to fetch. And if count is 0, then we will just put those through. So then we know that this A7 is something that we want to have in our byte sequence. So we will just put in the next character plus the A7. And then we will look at this the second byte, the third byte in the sequence. So the second byte should be A7. The third byte is how far back should we look? So we will have a short pointer back, a couple of words, And then we will take that, and our starting position is the current position minus that ago times 2, because it's words. So that many words before is our starting position. And then we will copy as many as count words forward into our sequence. So we take the output sequence and put more characters from the previous characters in the output sequence. So this is a short jump back. But he also realized that sometimes you want to go back even further. So we want to go back really far in the sequence. And then is when you have a long jump, a long pointer. So this is the A8 pointer. So we do the same here, but we have more data. So we are looking for more than 3 bytes in the sequence left. And we look at the second byte, and if it's A8, and we do the same thing here. If we figure out that the count is 0, then we just want to put in those 2 bytes here instead in the sequence. And we see that we do that backwards. So we first put in the 3rd byte and then the second byte. And then we want to take a long one. And then the long one is actually starting from the beginning of the full byte sequence. So we will copy a range of all bytes from the I position 2, so the to I position 4. So that is the start BB. So that we will copy a couple of bytes here. So the second to the 4th byte, we will copy those in little endian, and then we will get the word there times 2. That is how many words from the beginning of the file that we want to jump in and have as our starting position. And then we do the same here. We put characters and get the characters from the start position plus the actual count. And we will put those chars in. And then when everything is done, we will put and if none of these are true, of course, then the current byte is just put in into the output buffer as is. And when we're done, we will take this this output buffer that we have and write to an output byte. So we will get some bytes and return those. So that is the way of uncompressing Carmac. Then we send that into a RLEW. And RLEW is just looking ahead instead. So it's pretty much a way if we have a sequence that is like this, and then we get a bunch of ones, then we will count these ones, 1, 2, 3, 4, 5, 6, 7, 8, 9. And in this case, we then put in the character and then 1 9 times. So that is pretty much how this function is working. So let's look at the code. We will take it in and wrap it in little endian. We will get the uncompressed size again. We will create a buffer of the uncompressed size. And then we will go through everything until the uncompressed size -2. We will get one word and check if it is this ABCD, which is this this byte where we are looking for in order to see if we need to write a longer sequence. And if it is that, then we will get another character, another word, that is our count. And then we will get a value. This is what we need to write. So for this count, until the number of count we have, we will put this value. And if the position is smaller than uncompressed size, we will break. Hopefully we will not get that condition. And then we have this output char here. If this is not true, we will just put the word in. So it's a very simple function. And then we have the same here to create it back to bytes from that buffer. So now we have our buffer and we want to send that data into Minecraft. So sending the map is pretty simple. We are using localhost. We are using the port for the server, which is 4711. And we will create the socket. So what we will do is write different commands to the socket as just lines of text. So it's a very simple interface here. We'll open a socket, we will open a print writer, and then I will just print this world set block. So in the world set this huge amount of blocks to 0. So it's pretty much set a bunch of air up here. And then I will set a large, similar sized thing to just rock. And then I will carve out air inside of that rock. So this is just a setup in order to create the larger world or the larger map placement. And it's just a really huge space that is larger than 64 times 64. And then we will go through and take the map data here. We will go through all the maps. So 64 times 64, we will do X and Y positions. We will fetch one map character and we will check what is this map character. And it could be a bunch of different things. And you see that I have mapped up everything here into what it should do. So first off, we have an elevator, for instance, and I want to write a diamond block as the elevator. So the draw wall will pretty much print in that particular block and the alternative to all the positions here. So we go X and Y, and then we are using X and Y for X and Z in the map world. And then we will use the Y coordinate 0, 1, 2, and 3. So we have a 4 block high map print. And 0 is the floor, 1, 2 is where the character is, and 3 is the ceiling. So it's very simple way of printing a wall here. And we were printing a bunch of different things, and I have mapped up all the Minecraft blocks. So here we have a bunch of Minecraft blocks that I've mapped up in this file. So here I have gone through and found a bunch of them that could be useful to use. And I also have gone through and mapped all the different kinds of Wolfenstein blocks that you can have and their numbers. So mapping them together and finding something that is reasonable is not that hard. But yeah, it took a while to figure this out. And I have done a reasonable job. There is a bunch of things that are not available in Minecraft that is used in Wolfenstein. And again, we had the problem with creating doors. It's just a never-ending problem for me. Sending the entities, I have done similar things here. I have mapped up wolf objects. So we have a bunch of different wolf objects here. All the different enemies, and I haven't mapped up many enemies that you see here. The only one I've mapped up is the standing guard and the patrolling guard, and those are zombies, and that is hard enough. I have not been able to get through the first level with just those enemies. And then we have mapped up food, medkit, ammo, cross, crown, and life. It's just treasures and so on. And the player I have mapped up as well, of course. So the first part here is just where the player should be. Player, set tile, and particular position. And then I have sending a block and sending a crafting table, for instance, to send a block to this position. Flower pot, dog food, and so on. So there is a couple of those that I have mapped up. Going through all of those would be pretty tedious. I will not do that. So this is pretty much what I went through. We can load map 0 here, for instance. So if I run this, now it's running a different file. So let's stop that. Let's run this particular one. So we see here that we load wolf1 map 1. And there it has loaded the entities as well. So if I switch back to Minecraft here, I are in the world in map 1. And here we see all the zombies. I have no sword or anything to protect myself. So let's see if I can just run through here and get to the end. The The doorways are really hard. Let's see. Oh, another zombie. Oh, a small zombie as well. So zombie child. So you see, it's really hard to get for the first level. But I can just go here and say I want level 10 instead. And it will reload. So now I have, well, Wolf 2 map 1. So the first map of the second episode of Wolfenstein. And if I respawn here, let's see. Didn't it load? Let's see if I get inside of the map again. Now it goes. So now we see we have a totally different map here from Wolfenstein. A lot of dirt here. Dirty walls, I guess. And I don't know this map. Oh, some cake. Always great. So I have never played this map. I haven't played the original even. So finding my way through here without running into any enemies will be really hard. But you can see here that it really works. I can really load any Wolfenstein level and play around with it. And you can map it up your way. You can have it any other way if you want. And play around with where things should be placed and what kind of entities you want to use. I got lost. So, that was what I wanted to cover today. I hope that you found this interesting. I hope that you learned something today. It was a lot of fun for me, at least, to figure out how the different compression algorithms worked. So the RLEW is really interesting for some applications where you have a lot of bytes, words, or similar things that are similar in a sequence. So you can just replace them with this counter. So that is very useful for some applications. And of course, there's Carmacized thingy where you're looking at a buffer that you have already written in order to figure out how you can compress things even further. The reason why he didn't use Lempensieve or any of the ones that are already invented, so Lempensieve and so on was invented in the 70s, but the reason he didn't use those was because he was memory constrained and CPU constrained. So he needed to have something that could use a lot less memory and also be very fast in order to render these maps. So he did his own in order to accomplish that. I hope that you found this interesting. I hope that you learned something today. If you like this video, give it a like, share it with your friends and colleagues. If you want to support the channel, there is link in the description for donations or affiliate links. If you have any comments or suggestions, leave those in the comment section down below. And I really hope to see you